from GATE exam. So whatever the problems have come, from this you will understand the level of problem which are appearing in GATE exam. Okay. From the beginning, first problem. This problem has appeared in GATE 1991. A signal flow graph is given. Okay. Minus 1, minus 1, minus 1. For this signal flow graph, find gain C by R. Okay, now to solve this, we have to use the Mason's gain formula for this. We have to see the number of forward paths, and for the each forward path, we have to look for the linked loop connected with that forward path. Okay. C by R according to Mason's gain formula is forward path upon 1 minus sum of all the single loop taken one at a time, then 2 non-touching loop taken 2 at a time. Both we have to take. Okay, like this, then taken 3 at a time, then taken 4 at a time, sum of all the non-touching loops. In the present figure, forward path 1 is 2 into 3 into 4 plus 5 times. With this forward path, I have one non-touching loop which is minus 3. Okay, then the denominator 1 minus all the single loop, minus 2, minus 3, minus 4. Okay, then the loops taken, one more is there in this, minus 5. Okay, then the two non-touching loops, minus 2 into minus 4. Okay, rest all have, rest nothing is there. So from this I can calculate, this is 2 into 3 into 4 which is equal to 24 plus 1 minus minus 3 is equal to 4. 4 into 5 is 20 upon 1 minus minus 2 minus 3 minus 4. This gives me minus 9. Minus 9 minus 5 minus 14 plus 8. This is equal to 44 upon 14 plus 1 plus 8, 23. So 44 upon 23 is the answer for this. Okay, simple problem. Just we have to see the number of forward path and the loops attached with this. This is one loop, this is another loop, this is another loop, this is again one more forward loop. To this forward loop, this loop is non-touching. Okay, so that's why we have taken this in this. Okay, minus 3 is the sum of this, 3 into minus 1. Okay, so this was one problem. Again one more problem. Again this problem has appeared in GATE 1991. A second order transfer function is given. Now a statement is given, if the system initially at rest is subjected to unit step input at t equal to 0, then second peak in response will occur at, we have to find the second peak. See, the output of this is going to come something like this. Okay, we have to find, this is my first peak, this is my second peak. This time I have to find, okay, t second peak. Now gs equal to 25 upon s square plus 8s plus 25. From this, omega n is equal to root 25, which is equal to 5 radians per second. Okay. Now the peak overshoot or undershoot happens at t max or min n pi by omega t. Omega t is the damping frequency, where n value 1, 2, 3 decides the minima or maxima. N equal to 1, 3, 5 gives peak, or we can say overshoot. N equal to 0, 2, 4 gives undershoot. Okay. Now it has become very clear. So for second peak, my n value is equal to 3. N equal to 3. Omega d will be how much? Omega d is nothing but omega n under root of 1 minus zeta square. So how much is zeta? 2 omega n, zeta equal to 8. So zeta equal to 0.8. This implies my omega d is equal to 5 times of 1 minus 0.8 whole square. This is equal to 5 into 0.6, which is equal to 3. Okay, thus t second peak is equal to 3 into pi by 3, which is equal to pi. Thus pi second is the answer for this. Simple. See once again. When I applied a step input to any second order system, my output is going to come like this. Okay. From this output I have to find this peak, the time a system takes to reach the second peak. So looking at the formula of this, for any maxima or minima, see here it is maxima, here it is minima, here it is maxima, here it is minima. So for any maxima and minima, my n pi by omega d is the general formula, where omega d is the damping frequency and n value can be 0, 1, 2, 3, 4, 5. So depending on the value of n, I will have either an overshoot or I will have either an undershoot. Okay, so we have to look that and we have to find the, so but just in case if we want to find the first undershoot, for the case of first undershoot, n value will be 2. At that time we are using 2 here. Okay, omega d value will be remain same, which is equal to 3. So 2 pi by 3 is the answer for the first undershoot. Okay, like this we have to continue and find the answer. Next question. The statement of this question is, the open loop transfer function of a feedback control system is open loop transfer function is given by 1 by s plus 1 cube. Okay, then find the gain margin. We have to find the gain margin for this. Solution. So what is gain margin and what is phase margin? See, the gain margin is a point at which phase is minus 180 degree. The value of gain at particular frequency at which phase is minus 180 degree. This value of gain, how much it is about the 0 dB, that is the gain margin. Okay, so at the frequency at which the phase is minus 180 degree, at that particular frequency if I find my gain, that will be the gain margin. Okay, now to find the value of frequency, first I need to find the phase of this. So the phase of GSHS, convert this to 1 by 3 j omega plus 1 whole cube. So the angle of this is minus 3 times tan inverse omega. Okay, this must be equal to minus 180 degree. So my omega is tan inverse omega is equal to 60 degree. Thus omega equal to root 3 radians per second. With this omega, I need to find my gain margin. So gain margin at omega equal to root 3, this omega is called phase crossover frequency, log of 1 by g of j omega h of j omega. Okay, so when I found this, log of this is 20 s plus 1 whole cube, 20 log of j omega plus 1 whole cube. Substitute omega by root 3, 20 log of j root 3 plus 1 whole cube. So this is equal to 20 log of 2 cube, which is equal to 3. 20 log 8 is the gain margin. So at frequency, at phase crossover frequency, that is at when phase is minus 80 degree, my gain margin is positive. Okay, the system is a stable system. From this we can find out about the stability and instability. So just for a note, you can write, for a stable system, gain margin and phase margin both should be positive. Okay, since this problem concerns about finding the gain margin, but if a problem is concerned about finding the phase margin must be positive for a stable system. Okay, with gain margin. While solving the problems, we will take care that the variety of problem is not repeating. Okay, now another problem, the same here statement. A unity feedback control system has the open loop transfer function. This is of course a negative feedback. Unless and until it is not mentioned about the type of feedback, assume it is a negative feedback. Gs is equal to 4 times of 1 plus 2s upon s square s plus 2. Okay. Now to this control system, if input is a ramp input, if the input to this system is unit ramp, Then we have to find the steady state error. Find steady state error. Okay, simple. Now what we can do in this? Error steady state is equal to limit s tending to 0 s into rs upon 1 plus gs into hs. Okay, so rs here is equal to 1 by s square, which is a Laplace transform of unit ramp. Okay, hs is equal to 1. Thus ess can be written as limit s tending to 0 s into 1 by s square upon 1 plus 4 times of 1 plus 2s upon s square into s plus 2 multiplied by 1. Okay, so this gets cancelled with this. So I am having limit s tending to 0 1 by s plus 4 times of 1 plus 2s upon s into s plus 2. On substituting the value of s, I will get this as 0. Thus steady state error in this case is 0. Simple problem, just we have to apply this formula. Okay, or directly we can find, since it is a unit ramp, so we have to find the velocity error constant kV. kV is nothing but limit s tending to 0 s into gs hs. So when we find this, I will get my kV equal to infinity. kV equal to infinity means my error by 1 by kV, which gives me 0. So this is the answer for this. Other way of solving this. Okay, this was one type of problem. Now, very good problem. Question number 5. Characteristic equation of a feedback control system is given. S cube plus 5s square plus k plus 6s plus k equal to 0. From this characteristic equation, treating for k value ranging from 0 to infinity, okay, if we draw the root locus diagram, if root locus diagram is drawn, then for larger value of k, the asymptotes of this root locus asymptotes of this root locus meet at a point in S plane at coordinate axis. We have to find those points. Okay. Firstly, this equation is written in the form of 1 plus GSHS equal to 0. Okay. So from this equation I can separate the k term and I can separate the s term. So it will become s cube plus 5s square plus 6s plus k times of s plus 1 equal to 0. I can write this as k times of s plus 1 upon s common s square plus 5s plus 6 equal to 0. Okay. So now my GSHS equal to k times of s plus 1 upon s into s square plus 5s plus 6. So the poles of this s equal to 0. Factorizing this, I will get minus 2 and minus 3. Okay, poles. 0 of this is minus 1. Okay, so number of poles is 3, number of zeros is 1, number of asymptotes equal to 3 minus 1 equal to 2. Okay, when the asymptotes, the point at which asymptotes intersects the coordinate axis, that point is called centroid. So centroid can be found easily by summation of poles minus summation of zeros upon number of asymptotes, which is equal to minus 2 minus 3 minus minus 1 upon number of asymptotes 2, minus 5 plus 1 upon 2 minus 4 upon 2, which is equal to minus 2. Okay, so this is the solution for the problem. Directly they have asked the, indirectly they have asked the centroid. We have, or directly if they can ask the centroid, then it becomes a easier problem. Okay, so that's why this question is a good question, because a simple thing is asked but in a different way. One more problem. This problem has appeared in GATE 1992. We will solve the problems appeared in GATE in 2-3 sessions. For this, a Bode plot is given. The rate of decay of this is minus 20 dB per decade. Okay, this value is 20. Find the transfer function. You have to find this. In this point is this. This point is 10. Now, very simple. Since it is initially it is constant and afterwards at 10 it has decreasing at minus 20 dB per decade, that means at frequency omega equal to 10, it has got one pole. Okay, so I can write my GS nothing but k times of s by 10 plus 1. For smaller values of k, so it will be the overall magnitude of g of j omega is equal to 20 log k minus 20 log omega by 10 whole square plus 1 by 2. For smaller values of omega, I can easily ignore this term. So 20 log k is equal to 20, which implies the k value is equal to 10. Thus g of s will become 10 upon s by 10 plus 1, which is also equal to 100 times of s plus 10. This is the answer for this. Simple problem. One more problem. I'll just write the problem now. We'll see the solution after this. Unity negative feedback system with open loop transfer function g of s equal to k times of s into s plus 1 s plus 2. For this we need to plot the root locus. Okay. Now if we look at this system, I have poles at 0, -1 and -2. So I can plot it. One pole at 0, one pole at -1, one pole at -2. So applying the rules of plotting the root locus, my root locus will lie in this region and my root locus will lie in this region. Since in this case there are no zeros, so all poles will terminate at infinity, since there are no zeros in this. If we look at this GS, second point, k times of s into s plus 1 s plus 2, if we apply the Routh criteria, then we can find there will be some values of k for which the system is unstable. Okay, s square plus s plus 2 plus k equal to 0, s cube plus 2s square plus s square plus 2s plus k equal to 0, s cube plus 3s square plus 2s plus k equal to 0. If I use now Routh criteria, 1 and 2, 3 and k, 6 minus k upon 3, 0, k. So k value must be greater than 0, and 6 minus k must be greater than 0, or k must be lesser than 6. So in this condition only my root locus will be in a stable region. After this it will become unstable. For value of k equal to 7, this is unstable. Okay. So if I come to my root locus, my two poles will come together. They will come at one point. That will be the breakaway point for this. This pole will also start moving towards infinity. After coming at this point, they will break apart, and at some value of k, the poles will move to the right hand side of the S-plane. So once the pole moves to the right hand side of the S-plane, this will make my system unstable. So the value of k at this point, k is equal to 6. K is equal to 6. And the value of k after this point, k greater than 6. K greater than 6. Value between here to here is k lesser than 6. Okay. So this way we can plot the root locus, and we can, if the choices are given, we can make out which is the correct one. Okay.